Section number 16 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Neilson, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 6, Program Options and Evaluation, Part 4. 6.5, Flexible Path Integrated Options Fit to the Less Constrained Budget. 6.5.1, Evaluation of Integrated Option 5. In the final family of options are those that pursue exploration using the flexible path strategy discussed in Section 3.5. Like the integrated options in Section 6.4, these are not constrained to the FY 2010 budget profile. Rather, they are fit to the less constrained planning budget that the committee developed. As shown in Figure 6.2.3-1, that budget profile increases to $3 billion above the FY 2010 guidance between FY 2011 and FY 2014, and then grows at a rate comparable to an expected inflation rate of 2.4% per year. Option 5, Flexible Path. This option follows the flexible path as an exploration strategy. It operates the shuttle into FY 2011, extends the ISS until 2020, and funds technology development. In all three variants, as shown in Figure 6.5.1-1, the commercial transport service becomes available in the mid to late 2010s. To begin ferrying U.S. crew to the ISS. By the early 2020s, after the heavy lift vehicle is developed, development of a small in-space habitat and an in-space restartable propulsion stage follows. All three variants also include a hybrid lunar lander that is smaller than the Altair. See Figure 6.2.2-2. The ascent stage is developed by NASA, but the descent stage is assumed to be commercially developed, building on the growing industrial capability pursuing NASA's Lunar Lander Challenge and the Google Lunar X Prize. The commercial lander could also use the NASA-developed in-space restartable engine that would be used for missions on the flexible path. There are three variants with this option. They differ only in the heavy lift vehicle. Variant 5A as the Ares 5 Light variant. It develops the Ares 5 Light, the most capable of the heavy lift vehicles in this family of options. Figure 6.5.1-1 shows the schedule for this option. The Ares 5 Light becomes available in the early 2020s, and the flexible path missions to the Moon, Earth escape to Lagrange points or near-Earth objects, and a Mars flyby occur at about 1-year intervals. Initial lunar landing takes place in the mid to late 2020s. Lunar buildup occurs at a rate of about 2 flights per year with the more capable Ares 5 Light. On-orbit refueling or the use of a second Ares 5 Light is necessary for the most energetic of the flexible path missions. Variant 5B employs an EELV Heritage Commercial Super Heavy Lift Launcher and assumes a different and significantly reduced role for NASA. It has an advantage of potentially lower operational costs, but requires significant restructuring of NASA. It follows the same timeline as Variant 5A up to the landing on the Moon. On-orbit refueling is used for the flexible path missions. Therefore, the EELV Heritage Super Heavy flies 2 missions of 3 launches per year to the moon, but does not carry as much load on each mission unless on-orbit refueling is used. Thus, a slower lunar development or the development of a less massive lunar infrastructure results. Variant 5C uses a directly shuttle-derived heavy lift vehicle, taking maximum advantage of existing infrastructure, facilities, and production capabilities. It too follows about the same timeline up to the first lunar landing and uses on-orbit refueling for flexible path missions. When lunar missions begin, the higher recurring cost of the more directly shuttle-derived heavy launcher causes a slower rate of lunar buildup. Comparison of the 3 flexible path valuations is shown in Figure 6.5.1-2. The distinguishing features are the Ares 5 Light option 5A has an edge in exploration preparation due to the more capable vehicle and in mission safety challenge because the more capable vehicle requires less complex ground and on-orbit operations. The EELV Heritage Super Heavy option 5B has an edge in technology because it includes a new US-developed large hydrocarbon engine and the lowest, i.e. best, life cycle costs due to the commercial nature of this operation. It does poorly in sustainability due to the disruption in contracts, workforce transitions, and the new way of doing business that would be necessary at NASA. The more directly shuttle-derived heavy launcher in option 5C has an edge in sustainability due to advocacy for shuttle-derived systems, but does poorly in life cycle costs. 6.5.2 Examination of the key questions on Ares 5 family versus shuttle-derived heavy launcher. In section 6.4.3, the decisions on heavy lift were outlined, and the comparison between the Ares 5 and Ares 5 Light was discussed. In this section, the comparison between the Ares 5 family and the more directly shuttle-derived launcher, as indicated by the decision tree of Figure 6.4.3-1, will be examined. The background for these decisions was presented in Section 5.2. As discussed in Section 6.4.3 above, the 2 Ares 5 family launchers under consideration are the Ares 5 with 5.5 segment SRBs and 6 RS-68 family engines, and the Ares 5 Light with 5 segment SRBs and 5 RS-68 family engines. In comparison with the directly shuttle-derived vehicles, these differences among the Ares 5 family are small. Also discussed in Section 5.2, the primary candidate for consideration from the more directly shuttle-derived family is the inline variant. This vehicle uses 2 4-segment SRBs, some number of Space Shuttle main engines, SSMEs, or the engine's expendable derivative, the RS-2E, 3 or 4 typically, on the bottom of a re-engineered 8.3 meter diameter tank with an inline EDS and on top a cargo payload or human carrying capsule with a launch escape system. To the less trained eye, such a vehicle would look much like an Ares 5. In fact, at the end of the ESAS study in 2005, the candidate for the CALV cargo launch vehicle was exactly the shuttle-derived variant just described. In the 4 years since ESAS, The design has evolved into the Ares 5 known today. Thus, the considerations for this choice of a more directly shuttle-derived vehicle versus Ares 5 more or less exactly play out the trade studies conducted by NASA in the last 4 years. The principal difference between the two families in the use of the SSMEs or their expendable derivative on the more directly shuttle-derived launcher versus the use of the RS-68 family engines on the Ares 5. The use of more shuttle-derived components lowers the development costs somewhat and accelerates by about a year the availability of heavy lift, but these dates of first availability of heavy lift are in the early 2020s at best, due to budget constraints and likely extension of the ISS. Therefore, even if a shuttle-derived vehicle is developed and the shuttle is extended, there is about a decade of gap in heavy vehicle operations. This erodes the benefit of using the shuttle extension and a more directly shuttle-derived vehicle to close the critical workforce gap. Using the more directly shuttle-derived vehicles does produce a somewhat less capable vehicle, figures 5.2-2 and 5.2.1-1, and increases the reoccurring costs for a given mass launched to low Earth orbit. For example, in a year of planned constellation lunar operations in the mid-2020s, there would be 3 shuttle-derived vehicle launches for each mission to the moon, which would deliver a mass comparable to that of 2 Ares 5 class launchers. Cargo missions would use 1 or 2 shuttle-derived launchers, with 2 crew and 2 cargo missions per year. This would require 8 to 10 launches of the shuttle-derived launcher, each with 3 or 4 SSMEs or derivatives, for a total of 24 to 40 of the shuttle engines being used, with a resulting high recurring cost. Among the other notable differences between the Ares 5 family and the more directly shuttle-derived launcher family is the mission launch reliability. Since the latter requires 3 launches for each planned constellation lunar mission, there would be a somewhat lower reliability in any given time window than would be provided by the Ares 5, which only would require 2 launches in the same time window. The committee considered as an issue the commonality with the National Space Industrial Base. The Ares 5 uses engines from the RS-68 family, with commonality in the industrial base with those used on the EELVs by National Security Space. Both the Ares 5 and the more directly shuttle-derived vehicle have commonality in the solid rocket motors with vehicles used in national security space. In summary, the committee viewed the decision between the Ares 5 family and the shuttle-derived family as one driven by cost and capability. The development cost of the more shuttle-derived system would be lower, but it would be less capable than the Ares 5 family and have higher reoccurring costs. There are potential workforce and skill advantages associated with the use of the more directly shuttle-derived system, but the long gap between when the shuttle is retired in 2011 or even 2015 and when the shuttle-derived heavy launcher becomes available in the early to mid-2020s would diminish the potential value of the workforce continuity associated with shuttle derivatives. 6.5.3 Examination of the key question on NASA heritage versus EELV heritage super heavy vehicles. The highest level decision on heavy lift launch vehicles is whether to base the launch system for exploration on these NASA heritage vehicles or on the further extensions of the EELV heritage vehicles up to the 75 MT range, figure 6.4.2-1. It should be emphasized that this is not the existing EELV heavy launcher, which has a maximum payload to low Earth orbit of about 25 MT, but rather requires the development of a substantially new vehicle in part of existing components and manufacturing facilities. The EELV Heritage Super Heavy Launch Vehicle would be capable of launching about 75 MT to low Earth orbit, significantly less than the Ares 5 family at 140 to 160 MT, or the shuttle-derived vehicle in the range of 100 to 110 MT. However, the EELV Heritage Super Heavy is still larger than the committee's estimated smallest possible launcher to support exploration, which is in the range of 40 to 60 MT. In a nominal piloted lunar mission without in-space refueling, the EELV Heritage Super Heavy would require 3 flights, potentially with an additional crew taxi flight, versus 2 launches for the Ares 5 Lite. In the flexible path options, the EELV would not require more launches, but would involve more on-orbit operations than Ares 5 family approach. For these launch rates, the EELV would have a lower recurring cost than the NASA Heritage vehicles. Initially, the EELV Heritage Super Heavy vehicle would use the Russian RD 180 hydrocarbon-fueled engine, currently used on the Atlas V. In the cost analysis utilized by the committee, provision was made for the development of a new large domestic engine to replace the RD 180 for both NASA and national security missions. This would have technology benefits and would provide value to national security systems. While there are technical differences between the two families, the committee intended the principal difference to be programmatic. The EELV Heritage Super Heavy would represent a new way of doing business for NASA, which would have the benefit of potentially lowering development and operational costs. The committee used the EELV Heritage Super Heavy vehicle to investigate the possibility of an essentially commercial acquisition of the required heavy launch capability by a small NASA organization similar to a system program office in the Department of Defense. It would eliminate somewhat the historic carrying cost of many Apollo and Shuttle era facilities and systems, thus creates the possibility of substantially reduced operating costs, which may ultimately allow NASA to escape its conundrum of not having sufficient resources to both operate existing systems and build a new one. However, this efficiency of operations would require significant near-term realignment of NASA, substantial reductions in workforce, facility closures, and mothballing would be required. When the committee asked NASA to assist the cost of this process, the estimates ranged from $3 billion to $11 billion over 5 years. Because of these realignment costs, the EELV Heritage Super Heavy does not become available significantly sooner than the Ares 5 or shuttle-derived family of launchers. The transition to this way of doing business would come at the cost of cutting deeply into the internal NASA capability to develop and operate launchers, both in terms of skills and facilities. There would be other consequences at the national level. Needless to say, the co-development of the EELV Heritage Super Heavy would require careful coordination between NASA and the Department of Defense to ensure joint value. In summary, the committee considers the EELV Heritage Super Heavy Vehicle to be a way to significantly reduce the operating cost of the heavy lifter to NASA. In the long run, it would be a less capable vehicle, but probably sufficiently capable for the mission. Reaping the long-term cost benefits would require substantial disruption in NASA and force the agency to adopt a new way of doing business. The choice between NASA and EELV Heritage is driven by potentially lower development and operations costs, favoring the EELV Heritage system, versus continuity of the NASA system design, development, and mission assurance knowledge and experience, which would provide higher probability of success and predictable developments favoring NASA systems. EELV Heritage launch systems, due to their lower payload performance, would require significantly greater launch and mission complexity to achieve the same total mass in orbit. The EELV option would also entail substantial reductions in the NASA workforce and closure of facilities necessary to obtain the expected cost reductions. 6.6 Comparisons across integrated options. 6.6.1 Cross-option comparisons. A cross-family comparative evaluation is shown in Figure 6.6.1-1, which contrasts the baseline, option 3, with the Ares 5 light variant of the flexible path, option 5A. The flexible path option scores more highly than the baseline on 9 of the 12 criteria. The higher rankings include exploration preparation due to much more capable launch systems, technology due to investment in technology, science because of more places visited, human civilization due to the ISS extension, economic expansion because of commercial involvement in space elements and crew transport, global partnerships gained by extending the ISS, public engagement by visiting more new locations and doing so each year, schedule, exploring beyond low Earth orbit sooner, life cycle costs due to commercial crew services. 6.6.2 Examination of the key question on exploration strategy. The fifth and final of the key questions guiding the decisions on the future of human spaceflight is: what is the most practical strategy for exploration beyond low Earth orbit? In Chapter 3, 3 exploration strategies were presented, but the choice of exploration of Mars first was found not to be viable at this time. The 2 remaining choices are Moon first on the way to Mars, with surface exploration focused on developing capability for Mars, flexible path to Mars via the inner solar system objects and locations, with no immediate plan for surface exploration, then followed by explorations of the lunar and or Martian surface. This contrast can be highlighted by comparison of the reference variant for Moon first option 4A and flexible path option 5A, as shown in Figure 6.6.2-1. These 2 options differ only in exploration strategy. The flexible path equals or exceeds the ratings of the Moon first option in all areas. It has an advantage in science, economic expansion, public engagement, and schedule. These front distinctions will be examined below. From the perspective of science knowledge, the moon first approach would allow better understanding of the evolution of the moon and the moon's surface as a record of events in the evolution of the solar system. The flexible path would explore near Earth objects and also demonstrate the ability to service science observatories at the Lagrange points. The crews on such missions would potentially interact with robotic probes on the surface of Mars, returning samples as well. In some of its alternatives, including the one costed in Section 6.5, the flexible path also allows exploration of the moon, though at a more limited scale than in the moon first approach. Considering that we have visited and obtained samples from the moon, but not near Earth objects or Mars, and also that the flexible path develops the ability to service space observatories, the science knowledge criterion slightly favors the flexible path. Broadly, the more complex the environment, the more astronaut explorers are favored over robotic exploration. In practice, this means the astronauts will offer their greatest value added in the exploration of the surface of Mars. It is likely that the flexible path approach would engender more public engagement than the moon first approach. In every flight, the flexible path voyages would visit places where humans have never been before, with each mission extending farther than the previous one, potentially heading to a full dress rehearsal for a Mars landing. A potential liability of the moon first option is that it could appear to some stakeholders as a modern repetition of exploration that was accomplished 50 years earlier. Schedule also favors the flexible path scenario. The fundamental economics of the investment by NASA to begin flights on the flexible path and moon first options are shown in Figure 6.6.2-2. Before lunar exploration can begin, NASA must complete 4 development programs: the Heavy Lift Launcher, the Orion capsule, the Altair lander, and at least some of the lunar surface systems. Even the well-funded Apollo program only had to complete the first 3 of these. In contrast, exploration on the flexible path could begin with just the capsule and launcher, and then slowly develop much less costly in-space propulsion stages and habitats. After NASA explores on the flexible path for a half decade or so, it could then invest in the lunar lander and surface systems. In summary, the flexible path provides for exploration beyond low Earth orbit several years earlier and allows a less demanding programmatic investment profile. Because the flexible path option contained a commercially developed lunar lander descent stage, it was evaluated more highly in economic expansion as well. The use of a commercial lander is not fundamental to the execution of the flexible path, but is more likely in this strategy. The lunar landing would be later, involve a simpler lander, and follow the development by NASA of the in-space restartable engine, of which would make a commercial system more viable in the flexible path than in the moon first strategy. On the evaluation criteria on which the two strategies score equally, there are some distinctions. under human civilization both lead to better understanding of human adaptation to space, but the flexible path aids in the protection of Earth from near-Earth objects. From the viewpoint of mission safety challenges, the two strategies are also about equal. Operations at the moon are closer and allow return to Earth more rapidly, but landing on and launching from a surface is a dynamic environment. In contrast, the flexible path missions are less dynamic, but occur farther from Earth. There is no reason to believe that the remaining evaluation criteria favor one or the other strategy for exploration. They have more to do with how the strategy is implemented. For example, either the moon first or flexible path could be the basis for a new or extended international partnerships in space. In summary, 8 of the 12 criteria favor neither the moon first nor flexible path strategies for exploration. However, of the 4 that do discriminate, science knowledge, public engagement, schedule, and life cycle costs all slightly to moderately favor the flexible path. Finding on evaluation of program options. Options for human spaceflight should be evaluated by a set of criteria that are consistent with goals. The committee identified 12 criteria which measure the capability of an option to satisfy its stakeholders along the motivations listed above, along with programmatic issues of safety, cost, schedule, sustainability, and workforce impact. It is the role of decision makers to prioritize these measures. Findings on options for the human spaceflight program. The committee developed 5 alternatives for the human spaceflight program. In reviewing these, it found human exploration beyond low Earth orbit is not viable under the FY 2010 budget guideline. Meaningful human exploration is possible under a less constrained budget, ramping up to approximately $3 billion per year in real purchasing power above the FY 2010 guidance in total resources. Funding at the increased level would allow either an exploration program to explore the moon first, or one that follows a flexible path of exploration. Either could produce results in a reasonable time frame. End of section 16. Recording by Lynda Neilson, Vancouver, BC.
Section 17 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Section 17. Chapter 7. Critical Technologies for Sustainable Exploration. The Space Act of 1958 calls on NASA to preserve the U.S. position as a leader in space technology. Today, the alternatives available for exploration systems are severely limited because of the lack of a strategic investment in technology development in past decades. Looking forward, NASA has before it an unprecedented opportunity to make an effective strategic technology plan. With a 20-year roadmap of exploration laid before it, NASA can make wise technology investments that will enable new approaches to exploration. 2 recent reports of the National Academies have made recommendations in this regard. The investment should be designed to increase the capabilities and reduce the costs of future exploration. NASA has conducted studies to demonstrate the mass reduction and therefore operational cost savings that are achievable with investments in technology. Figure 7.1-1. With technology investments, the mass required for a Mars exploration mission decreases from 8 times the mass of the International Space Station to a mass comparable to the station. Notes: results are cumulative, and thus trends will be different for different technology combinations and sequences. The change between points shows the relative mass savings for that particular technology. 2018 one-year round-trip mission, crew of 4, lander pre-deployed. All propulsion chemical, aero capture, advanced propulsion, closed-loop life support, advanced materials, maintenance and spares, advanced avionics. As an illustration, it indicates an almost tenfold reduction in mass required for future missions to Mars. If appropriately funded, a technology development program would re-engage the minds at American universities, in industry, and within NASA. This will benefit human and robotic exploration, the commercial space community, and other U.S. government users alike. 7.1. Fundamental unknowns. 3 factors affecting long-duration human space exploration are of central importance, yet do not lend themselves to definitive assessment based on the available data. 1. The effects of prolonged exposure to solar and galactic cosmic rays on the human body. 2. The impact on humans of prolonged periods of weightlessness, followed by a sudden need to function without assistance in a relatively strong gravitational field. And 3. The psychological effects on individuals facing demanding tasks in extreme isolation for well over a year with no possibility for direct outside human intervention. While the specific technologies to address needed capabilities can and will be debated, if the United States wishes to conduct more and more capable missions in the future with near constant budgets, it is essential to develop and bring to flight readiness the technologies required. This will not happen without a sustained plan in which needed capabilities are identified, multiple competing technologies to provide that capability funded, and the most mature of them demonstrated in flight so that exploration architectures can then depend on them. For many technologies, it is less expensive to design a flight demonstration using the facilities on the International Space Station than it would be to design a free-flying mission for each and every technology demonstration. Radiation effects on humans. Beyond the shielding influence of the Earth's magnetic field and atmosphere, ionized atoms that have been accelerated to extremely high speeds in interstellar space fill the solar system. The effects of such galactic cosmic radiation on crews on long-duration spaceflight far from the Earth are a significant concern. Additionally, normal solar flare activity also occasionally releases radiation potentially injurious to humans. On the Moon or on the surface of Mars, techniques are available to shield a human habitat from these sources of radiation, but the massive shielding is cost-prohibitive for a spacecraft. These radiation effects are insufficiently understood and remain a major physiological and engineering uncertainty in any human exploration program beyond low Earth orbit. A 2008 report by the National Research Council concluded, quote, lack of knowledge about the biological effects of and responses to space radiation is the single most important factor limiting the prediction of radiation risk associated with human space exploration, unquote. A robust research program in radiobiology is essential for human exploration. Research on these radiation effects on humans is limited on the International Space Station, since it is partly shielded by the Earth's magnetic field. In addition to studying the effects of galactic cosmic radiation, GCR, there are mitigation strategies, such as more effective shielding techniques or the use of high shielding mass on a reusable habitat that cycles between Earth and Mars without being accelerated for each mission, cycler habitat, that need additional study. Micro and hypergravity effects on humans. While significant data on crew adaptation to microgravity now exists from extended International Space Station stays, there is a need to further develop countermeasures and build an understanding of even longer profiles that will be encountered in exploration beyond low Earth orbit. The International Space Station is a logical place to conduct such research and the United States should obtain these data before the International Space Station is retired. Psychological effects of extreme isolation on humans. While many experiments have been conducted on Earth to examine the effects of prolonged isolation on humans needing to continue to function at a high level, these experiments generally fall short of simulating the circumstance of extreme physical confinement in which the participant realizes there is no opportunity to end the experiment. In this regard, missions to Mars would be far more demanding than those to the Moon. Mars, at its closest, is 56 million kilometers from the Earth, whereas the Moon is 380,000 kilometers. In the latter case, return is generally possible within a few days. In contrast, Martian circumstances may require many months or years for an emergency return to Earth. 7.2 Propellant Storage and Transfer in Space. Wernher von Braun wrote of the significant benefits to be gained from propellant transfer and storage in space. Up to this time, the normal approach for inserting payloads on trajectories away from low Earth orbit towards the Moon or Mars is to use an upper stage called an Earth Departure Stage, EDS. In the conventional scheme, the Earth Departure Stage burns some of its fuel on the way to orbit and arrives at low Earth orbit partially full. The remainder of the fuel is expended injecting the payload towards its destination beyond low Earth orbit. An alternative discussed in Chapter 5 is to refuel in space so that the EDS can arrive in orbit mostly empty and be refilled. After leaving Earth, exploration systems will still need to make 1, 2, or 3 propulsive maneuvers, often after months in space. Again, past experience is to use storable propellants for these maneuvers, but in human exploration, the cost of doing this becomes large. The benefit of in-space cryogenic transfer and storage is that it enables refueling in space and the use of high-energy fuels for in-space propulsion. Using propellant transfer for the EDS, for example, allows more mass to be injected from the Earth with a given launch vehicle or a smaller launcher for a given payload. Today, these technologies are considered ready for flight demonstration according to both NASA and industry experts working in the field. Figure 7.2-1. Nonetheless, legitimate questions remain as to the practical feasibility of the approach. These concerns generally center on cryogenic transfer and storage technology. Cryogenic transfer, storage, and gauging in a microgravity environment create challenges that have been investigated by researchers in the laboratory for decades. Automated rendezvous and docking of delivery tankers has recently been demonstrated. Capabilities that remain to be demonstrated include long-term storage of very cold cryogenic propellant without excessive boil-off, transferring cryogenic propellant between tanks in a zero-G environment, making cryogenic fluid line connections, gauging the quantity of propellant in the tanks in a zero-G environment. Figure 7.2-2 shows the maturity of various technologies based on the NASA Technology Readiness Level, TRL, system, summarizing the current assessment of capabilities required for propellant transfer and storage on orbit. Figure 7.2.2 Technology Readiness of Components for In-Space Refueling. Source: Review of U.S. Human Spaceflight Plans Committee. Technology: Most mature approach. Status: Liquid acquisition. Surface tension device plus setting. Ground demonstrations. Needs flight test. Propellant gauging. Capacitance probe plus settling. Mature technology with settling. Ullage gas management. Settled vent. Mature technology with settling. Transfer line conditioning. Recirculation. Mature technology with settling. Automated fluid coupling. Extension of probe used for propellant couplings on Orbital Express. Flight demonstrated with storables. Needs flight test with cryogens. Insulation and thermal management. MLI is mature technology. Vapor-cooled shield further lowers boil-off. Ground demonstrations needs flight test. These cryogenic technologies have reached the point where a flight demonstration is the next logical step in development before this capability can begin to be designed into systems. The two technologies of liquid acquisition, collecting fluid in microgravity near the point from which it will be withdrawn from a tank, and automated fluid coupling cannot be tested in a realistic environment without in-space demonstration. Cryogenic coolers are needed for true zero-boil indefinite storage of liquid hydrogen, LH2, but other technologies listed in the table are intended to negate this problem for storage up to 1 year. 7.3. In situ propellant production and transport. After mastering the technologies for storing and transferring propellant in space, the next step is to manufacture propellant from resources already there. The lunar surface and some near-Earth objects are the only known sources of suitable resources that can be brought feasibly to cislunar space, such as to the Earth-Moon Lagrange point L1, which was identified as a promising candidate for a cislunar propellant depot in a 2004 NASA study. In situ propellant production requires the combination of two unique capabilities: 1. Producing the propellant, and 2. Transporting it economically. Oxygen is abundant in all lunar rocks and regoliths, dirt without organic material, and a variety of chemical processes to extract it have been demonstrated in Earth-based laboratories. These propellant production methods must next be demonstrated on the lunar surface through robotic missions. Collecting lunar material and bringing it to a lunar-based processing station presents a great challenge. Laboratory work has shown that this will likely require both robotic and human-tended missions to mature the technology. In addition, it is also extremely important to produce hydrogen for fuel in space. If hydrogen can be economically extracted from the Moon, it will likely serve as a source of propellant for future exploration missions. If it cannot be produced, the case for exporting propellant from the Moon becomes less compelling, and near-Earth objects would rise in importance. Discoveries in recent years do suggest the availability of significant hydrogen deposits at the lunar poles. In addition, Apollo samples showed useful hydrogen deposits from the solar wind implanted in the regolith. These regolith deposits would require processing large amounts of material comparable to coal extraction on Earth. Robotic exploration of the Moon continues today, and further interesting sources of resources may well be found. The composition of near-Earth objects is less well understood than the composition of the Moon because of the current dependence on telescope-based observations and inferences drawn from meteorites reaching Earth. These data suggest that almost any desirable resource can be found on near-Earth objects. But since each near-Earth object is a distinct body with its own orbit and properties, it is difficult to make generalizations about how resources would be extracted and returned to cislunar space. It is worth noting that in some cases, the energy required to return mass from a near-Earth object to near-Earth space is significantly less than to return mass from the lunar surface to Earth-Moon L1 Lagrange point. Therefore, further robotic exploration and human-tended pilot visits to near-Earth objects are particularly interesting subjects for future exploration. Reusable chemical rockets might also be used to deliver in situ propellant from the Moon to the Earth-Moon L1 Lagrange point. Space tugs carrying and using hydrogen are generally more compelling than tugs carrying and using other propellants. As an alternative, because of the Moon's low gravity, non-chemical propulsion should also be considered. Catapults, tethers, and beamed energy are likely to become practicable for lunar to L1 transport long before they become practicable for Earth to orbit launch, and should continue to be investigated. Nonetheless, their application appears to be far off. Because about 2/3 of the mass on an Earth to Mars to Earth mission would be propellant, cost-effective lunar-produced propellant could decrease the mass that must be lifted from Earth by a factor of 2 to 3. Further, achieving industrial levels of oxygen and hydrogen production on Mars would greatly simplify the challenge of transporting fuel for the return trip from Mars to Earth. In situ propellant produced on Mars has been considered as well. Oxygen could be extracted from the carbon dioxide-based Martian atmosphere, and both oxygen and hydrogen could be extracted from Mars' ample ice. Although laboratory work for extracting resources from Mars is promising, the technology remains to be demonstrated under realistic circumstances. 7.4. Mars orbit to surface transportation. The entry, descent, and landing of cargo on Mars is difficult because Mars has sufficient atmosphere to drive the design of landing systems, but inadequate atmosphere for feasible parachutes or wings to safely land astronauts on the surface. Scientific probes landing on Mars have used a complex mix of aerodynamic braking and rocket propulsion. These techniques will have to be improved before larger robotic or crewed missions can be sent to Mars. This research and technology development program needs to be started soon because it will require many iterations and increasingly larger missions before NASA is ready to demonstrate a safe, crewed Mars landing. Meanwhile, the intermediate results would greatly benefit future robotic missions. Because of the unique landing challenges posed by Mars, a robust human presence will require an advanced Mars orbit to Mars transportation system, most likely a reusable system that could transport cargo and people between the Martian surface and a depot located nearby. Nuclear thermal rockets using in situ Martian-produced propellant would fly to Martian orbit, collect a payload, and then use aerodynamic braking for the initial descent, followed by nuclear rocketry to land. Alternately, a chemical rocket would need to refuel on both Mars and in near-Mars space, such as on the Martian moon Phobos. Use of Phobos for propellant production would benefit transportation both to and from the Martian surface and provide the propellant for astronauts to return from Mars to Earth. A Phobos-based teleoperated exploration of the Martian surface, returning with samples from that surface, would likely precede a crewed Mars landing mission and would provide dramatically more responsive remote control than with the communication delays incurred between Mars and Earth. The use of Phobos and/or Mars-produced in situ propellant would likely reduce the flight cost of a crewed Mars landing expedition by a factor of 2 to 3. 7.5. Advanced space propulsion. Since the 1950s, advanced space propulsion has been recognized as an extremely desirable technology for Mars missions, as is the possibility of aero capture. See Figure 7.1-1. The application of advanced space propulsion to crewed missions could significantly reduce the amount of propellant used, while providing sufficient thrust to build up interplanetary velocities relatively quickly, over days or weeks instead of months or years. Unfortunately, the physics of the problem are such that the more a vehicle tries to minimize propellant usage, the more power it consumes. Yet, since the power supply weight increases with power generation requirements, a more substantial power supply can negate some or all of the benefits of lower propellant usage. Two promising advanced space propulsion technologies are based on solar and nuclear energy sources. Solar. Current solar power collectors are too heavy to deliver dramatic benefits in space propulsion. Solar electric thrust is used today for some satellites, and it may play a role in cargo transportation from LEO to, for example, L1 and back. Unfortunately, the acceleration it provides is so low that it would take months or years to get from Earth to the Moon, for example. As a result, for solar-powered advanced propulsion to provide revolutionary benefits, either far lighter, thin-film solar arrays must be matured, or the heavy solar power collector must be left off the spaceship and the power from the collector beamed by lasers to lightweight collectors aboard the ship. Theoretical studies indicate this latter technology is physically plausible, but it hasn't made it out of the laboratory. In addition, the beam can only be held together over distances up to a few 100,000 kilometers with a reasonable-sized transmitter. Solar technology requires research and development and flight demonstrations, as well as a large investment to build the solar power collector and beam transmitter in space. However, such an effort might pave the way for transmission of power to the Earth for domestic use, although it is not known whether such systems will prove economical even if they were to be technically feasible. Nuclear. A more mature technology, nuclear thermal propulsion, reached advanced ground-firing demonstrations during the 1960s, before the program was canceled. With nuclear thermal propulsion, a nuclear reactor heats hydrogen and then ejects it to provide thrust. A nuclear electric thruster, on the other hand, produces electricity to run an electric thruster, such as high-power Hall-effect thrusters or the Variable Specific Impulse Magnoplasma Rocket (VASIMR) thruster NASA is currently funding. Nuclear reactors today provide a substantial fraction of U.S. electricity production, and other countries use nuclear reactors to produce an even larger fraction of their domestic power. For advanced space transportation, much lighter nuclear reactors are required. Although expensive to develop, this solution could cut the cost of missions from Earth by a factor of 2 or 3. Alternately, it could be used to increase vehicle velocity for the same cost. Nuclear propulsion is probably essential for any crewed activity beyond Mars. The space nuclear program is an excellent candidate for a multinational research effort because different countries have different capabilities and research interests. NASA would benefit from a coordinated multinational research effort in this area. 7.6 Technology Summary. In order to give future designers a rich and effective set of technologies to draw from, an investment in a broad-based space technology program is prudent. This should be done in a focused but long-term manner, with a clear metric of enabling and reducing the cost of future exploration. There are a number of potential technologies and approaches to be examined, as indicated in Figures 7.6-1 and 7.6-2, which attempt to identify near and longer-term benefits from the investment. Some of these technologies have been discussed above, and others throughout the report. NASA would not be the only beneficiary of these technologies. Other U.S. government and commercial users of space would benefit as well in terms of new capabilities or reduced cost. Consistent with administration planning, the Earth-based benefits to economic recovery, energy technology, biomedical science and health, and protection of our forces and homeland have been indicated. Figure 7.6-1 Technology Opportunities to Impact Near and Midterm Exploration Capabilities and Sustainability. Source: Review of U.S. Human Spaceflight Plans Committee. Capability, Approaches, Benefit to NASA, Other benefits. Improved LEO launch. Higher volume production of expendables or reusables. Lower cost to LEO. NSS, ComS, Econ, Energy, Protect. Galactic cosmic and solar radiation mitigation. Better risk assessment, mitigation, shielding. Lower mass systems with better human protection. Bio. Autonomous rendezvous and docking. Improved sensors, algorithms, system tests. Enables unpiloted assembly and fueling in orbit. NSS, ComS, Econ, Protect. Cryogenic fuel transfer. Development and testing of fuel management and transfer technology. Enable smaller Earth departure stages or makes planned ones more capable. NSS, ComS, Econ, Protect. In-space restartable engine and boil-off technology. Cycle and engine development of hydrogen or methane engines. Enables longer duration exploration to destinations needing return propulsion. NSS, ComS, Econ, Energy, Protect. Crew autonomy and robotic support. Development of robotics to assist crew in space and on surfaces. Increases efficiency and focus of crew on tasks better done by humans. Protect. Advanced system design methodologies. Computational, simulation, and decision support systems. Quicker, better documented, and more thorough system designs. NSS, ComS, Econ, Energy, Protect. Advanced materials. High temperature and nano-engineered. Improves durability and strength. Lighter weight systems. NSS, ComS, Econ, Energy, Protect. Closed loop life support. Mechanical or biological systems. Lower mass for human duration. ComS, Econ, Protect. Methane engine. Cycle and engine development of methane engines. Allows better packaged stages that would use Mars ISUR products. NSS, ComS, Econ, Energy, Protect. Aero entry, descent, and landing in atmospheres. Development of novel structures for aero braking and entry. Lowers mass of systems, enables large masses on Mars. NSS, ComS, Econ, Protect. Technologies are listed in approximate order of decreasing importance and urgency. Other benefits are to national security space, NSS, commercial space, ComS, economic recovery, Econ, energy technology, Energy, biomedical science and health, Bio, and protection, Protect. Figure 7.6-2. Technology opportunities impact longer-term capabilities and sustainability. Source: Review of U.S. Human Spaceflight Plans Committee. Capability, approaches, benefit, other benefits. Surface systems, accessible or inflatable habitats and mobility systems. Lower mass to surface, more capable exploration. ComS, Econ, Protect. Surface power, advanced solar, isotope, or fissile-based. Lower mass to surface, more power for exploration and ISRU. NSS, Econ, Energy, Protect. Lunar in situ resource utilization. Regolith or hydrogen-rich formations derived. Lower consumable delivery to surface. ComS, Econ. Lunar in situ propellant production and export. Reusable lunar to EM L1 tug. Enabling of new Earth, Moon, Mars transportation architectures. ComS, Econ. NEO-based in situ resource utilization. Based on initial sample assays and transportation network. Enabling of new intersolar system transportation architectures. ComS, Econ. Advanced in-space propulsion. Beamed power or nuclear. Smaller in-space propulsion systems, significantly lower mass to LEO. NSS, ComS, Econ, Energy, Protect. Mars in situ propellant production. Atmosphere or ice derived. Lower mass for human duration and enabling of lighter ascent vehicles. ComS, Econ. Earth-Mars cycling spacecraft. Aldrin and multi-synodic cyclers. Enabling new mode of interplanetary travel. Finding on technology development. Technology development for exploration and commercial space. Investment in a well-designed and adequately funded space technology program is critical to enable progress in exploration. Exploration strategies can proceed more readily and economically if the requisite technology has been developed in advance. This investment will also benefit robotic exploration, the U.S. commercial space industry, the academic community, and other U.S. government users. End of Chapter 7. End of Section 17.
Section number 18 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Neilson, Vancouver, BC. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 8, Partnerships. Various forms of partnerships have been discussed throughout the report. This section examines in greater detail international partnerships, Section 8.1, as well as partnerships among elements of the U.S. government, Section 8.2. 8.1 International Partnerships. The human exploration of space is historically intertwined with the recent evolution of America's international relationships. The U.S. has moved from an era of competing with the Soviet Union in the Apollo era to collaborating with our historical allies in space station freedom, to embracing the Russians in the International Space Station, and now to engaging many potential new partners. Space exploration has become a global enterprise. Many nations have aspirations in space, and the combined annual budgets of the space programs of our principal partners are comparable to NASA's. See Figure 8.1-1. If the United States is willing to lead a global program of exploration, sharing both the burden and benefit of space exploration in a meaningful way, significant accomplishments could follow. Actively engaging international partners in a manner adopted to today's multipolar world could strengthen geopolitical relationships, leverage global financial and technical resources, and enhance the exploration enterprise. One means of reducing the funding demands of major human spaceflight programs is to join in partnerships with other nations that share common space goals. Thus far, 3 nations have by themselves placed astronauts in space: the U.S., Russia, and China. International programs offer the added advantage of providing access to advanced technology not available in the U.S., an increasingly common circumstance. Example, Russian-designed hydrocarbon RP-1 fueled liquid rocket motors. Such arrangements also facilitate cost sharing. The principal disadvantage of international programs, excluding business-to-business arrangements based on enforceable contracts, is the nations are sovereign entities and, as such, can unilaterally change their plans, which can be very disruptive. Much of the international community, probably justifiably, faults the U.S. with regard to this practice, but perhaps an even greater impediment to U.S. involvement in international cooperative programs is the U.S. International Trafficking in Arms Regulations, ITAR. The committee deems these laws to be outdated and overly restrictive for the realities of the current technological and international political environment. International programs are generally more difficult to manage than national programs, in part because of the need for a greater degree of consensus and coordination. However, this can often be overcome when one of the participating nations serves in a leadership role, as distinct from a domineering role. The management structure that has evolved for the ISS has proven particularly effective and can serve as the basis for the next major international cooperative human venture into space. The committee suggests that the president invite America's international partners to join with America in discussions of this possibility. The question occasionally arises whether the public would support space accomplishments shared among nations, as opposed to those representing purely American achievements. But the fact is that human spaceflight has always existed in an international context, first as competition and more recently as cooperation. It is difficult to argue against the latter. Moreover, the U.S. space program at its height had the self confidence to emphasize that the United States was acting as a representative of all humanity. The Apollo 11 plaque left on the moon reads, "Here men from the planet Earth first set foot upon the moon, July 1969 AD. We came in peace for all mankind." If international programs are to succeed, i.e., where a true partnership that benefits all parties exists, there will be inevitably some measure of dependency of the member nations upon one another. In some cases, this may imply dependency with regard to capabilities that lie on a mission critical path. Witness the impending launch gap. Nonetheless, if effective and meaningful partnerships are to be established, some degree of such dependency is simply the price of admission, a price the committee concludes that is worth paying in most instances. International cooperation has been fruitful for both robotic and human space missions. The U.S. has enjoyed long, positive space exploration partnerships with several countries. The U.S. has participated in cooperative efforts with Europe for many years, both through independent European country agencies and through the European Space Agency. Similarly, the U.S. has excellent historical space relationships with Japan and Canada. The U.S. Russian space partnership has roots in the Apollo Soyuz project of the early to mid 1970s. The current partnership began in the early 1990s with Phase 1 Shuttle Mir and continues today with Phase 2 ISS programs. The advantages have been noteworthy. Mir was revitalized and extended because of the capabilities of the Space Shuttle, and Russian assets provided U.S. logistics and astronaut transport to the ISS following the Space Shuttle Columbia's accident. In addition to synergies in space exploration, international civil space cooperation has provided positive grounds for fostering understanding between peoples and governments of partner countries. This committee believes that the existing partnership should be continued and urges the U.S. to consider expanding partnership by forming cooperative relationships with other countries, doing so within the current ISS partnership framework. This framework would serve as the foundation for international collaborations involving exploration beyond low Earth orbit. This position is consistent with the recent National Research Council report, America Future in Space, aligning the civil space program with national needs, which calls for enhancement of overall U.S. global leadership through global leadership in civil space activities. Specific recommendations address aligning international cooperation with U.S. national interests, which include expanding international cooperation and partnerships for the study of global climate change, the development of a body of law for a robust space operating regime, rationalization of export controls, expansion of the ISS partnership, continuation of international cooperation for scientific research and human space exploration, engagement of nations in educating their citizens for sustainable space technology development, and support for interchange among international scholars and students. Partner countries could develop planetary landers, Earth departure stages, habitats, and other significant systems and subsystems. As the lead partner, the U.S. could develop the Heavy Lift Launch Vehicle. This scenario would help divide costs equitably and elevate the prominence of partner countries. The committee notes that China has had an operational human spaceflight program since 2003, and India announced plans to launch astronauts into space using indigenous assets. The US and India have already begun cooperative activities in space. The Chandrayaan-1 spacecraft was flown to the moon in October 2008 with U.S. instruments on board. A number of nations are already developing capabilities that could significantly contribute to an international space exploration program. The U.S. has announced that it held preliminary discussions with China regarding joint space activities. It is the view of the committee that China offers significant potential in a space partnership. China has a human-rated spacecraft and booster system and is only the third country to launch astronauts into space. It has demonstrated advanced capabilities, including extravehicular activity on a September 2008 mission. China plans to fly the Heavy Lift Long March 5 vehicle before 2015, which it indicates will eventually be used to establish a space station, currently planned for initial launch in 2020. 8.1.1 International Space Capabilities. The following summarizes the extent of demonstrated activities in space by nations other than the U.S. Canada. The Canadian Space Agency, CSA, is a partner in the ISS with significant experience in human operations in space. CSA has specialized in robotics and teleoperated systems, but also has extensive experience in remote sensing, radar, on-orbit servicing, communications, and space science. China. As the third nation in the world to launch humans into space, the People's Republic of China, PRC, has developed an indigenous capability for the technical requirements associated with human spaceflight. The PRC has a stable of space launch vehicles up to medium lift capability, 9 MT to low Earth orbit, with upgrade to 25 MT envisioned, including the upper stage capabilities for geotransfer orbit and interplanetary trajectories. China has launched one robotic probe to the moon and has follow-on missions planned. The PRC has robust capabilities in communications, navigation, and Earth observation satellites. Next on its announced human spaceflight agenda are demonstrations of rendezvous and docking and the construction of an orbiting space laboratory. The PRC has demonstrated capabilities in life support, power generation and storage, pressurized module construction, in space propulsion and attitude control, guidance and navigation, and communications and computation. India. The Indian Space Research Organization, ISRO, possesses two very capable launch vehicles, and an upgrade is underway to provide a medium lift capability. India also has an indigenous capability to provide complex satellites and robotic scientific probes, as demonstrated by their first interplanetary robotic mission to the moon in 2008. A human spaceflight program is being strongly recommended to the Indian government by ISRO and is likely to be approved, which could lead to Indian human spaceflight capability as early as 2015. To date, the Indian space program has concentrated on telecommunications, Earth observation, and other low Earth orbit satellite programs. Japan. The Japan Aerospace Exploration Agency, JAXA, conducts a robust space program and is a partner in the ISS. Its workhorse launch vehicle, the H2, has been upgraded to the H2 transfer vehicle for use as a logistics carrier to the ISS. While the Japanese space program has a lower launch tempo than other major spacefaring nations, it has extensive capabilities, as demonstrated by the ISS Kibo laboratory, which includes teleoperated robotics. Japan has extensive experience in Earth and space science missions and telecommunications satellites, as well as in-ground base facilities for astronaut training, mission operations, communications, and tracking. Japan launched the very successful Cayuga lunar robotic mission in 2007 and has plans for follow-on lunar missions. South Korea. The Republic of Korea has its first space launch vehicle, developed with Russian assistance, ready for flight. Korea has flown as a spaceflight participant to the ISS via Russian launch and return, but has no other human spaceflight experience. The Republic of Korea has announced plans to develop a lunar orbit by 2020. Russia. Russia has a complete suite of space capabilities, from a robust launch vehicle stable to a broad spectrum of spacecraft design, production, and operation capabilities. Russia fields a number of space launch vehicles of proven design, from small through medium, 25 metric tons, to low Earth orbit, with various upper stage combinations that can provide payloads not only to low Earth orbit, but also to geotransfer orbit and to interplanetary trajectories. Russia is one of three nations to demonstrate the capability to launch humans into space. The highly evolved Soyuz spacecraft is currently programmed to become the linchpin of the ISS in the immediate future. Russia has also demonstrated capabilities in large space structures, pressurized modules, life support, power generation and storage, communications, thermal control, propulsion and attitude control, guidance and navigation, remote sensing, computation equipment, subsystems, and operation techniques. These are all elements necessary for both human and robotic space exploration. Currently, the Iran, North Korea, and Syrian Non-Proliferation Act, INKSNA, has limited cooperation in space operations between Russia and the United States. European Space Agency. The European Space Agency, ESA, and its member states possess very significant space capabilities. ESA is a partner in human spaceflight for the ISS and has demonstrated its ability to build large, pressurized, habitable modules for use as part of the ISS, as well as launch, rendezvous, and other critical capabilities. Through Arianespace, a French company owned by the French government, the Europeans possess the most active commercial space launch program in the world, with various launch vehicles up to medium capability, 21 MT, to low Earth orbit. They have demonstrated the capacity to put significant payloads on interplanetary trajectories and have demonstrated space navigation and communications for both low Earth orbit and interplanetary robotic probes. ESA possesses industrial and commercial capabilities to build complex spacecraft and robotic probes, including all subsystems. The automated transfer vehicle has provided significant logistics support to the ISS and has the potential to be upgraded to a cargo return vehicle and eventually a human carrying spacecraft. Individual member states also have interest in and the capacity for cooperation outside the ESA structure. Cooperation with both ESA and individual European states allows access to significant technological capabilities. Nations other than the above have very limited space programs, but could potentially play niche roles as their national industrial and technical capabilities allow. 8.2 U.S. Intra-Government Partnerships. The committee has examined issues about the space program managed by U.S. government agencies besides NASA, such as the Department of Defense, DoD, and the Commercial Space Office of the Federal Aviation Administration, FAA. Their focus includes the potential impacts of human rating, the current Evolved Expendable Launch Vehicles, EELV, as one option to reduce the post-shuttle launch gap. The FAA concentrates on the role commercial space companies can play in the space exploration program. A study sponsored by the Congress in July 2008 titled Leadership, Management, and Organization for National Security Space described the total U.S. space enterprise as including civil space, commercial space, and national security space, military and intelligence focused. All of these elements have overlapping capabilities, share technologies, and depend on a common industrial base. As a result, any examination of the U.S. human space program must consider its impact on the efforts of agencies responsible for these other U.S. space activities and vice versa. The most obvious concern has been expressed by the DoD, particularly the U.S. Air Force, because of its unique role today as the single agent for government expendable launch capabilities. The family of Evolved Expendable Launch Vehicles, EELV, Atlas the Fifth and Delta the Fourth, represent the primary heavy lift capability for the DoD and intelligence communities. Any changes in configuration to these EELV systems, such as incorporating crew escape systems in orbit, in order to human rate them, raised concerns about the potential impacts on cost and the ability to reassign vehicles from the EELV production line to high priority national security missions. The committee reviewed the technical changes required to human rate an EELV. It also met with the National Security Space leadership in the Office of the Secretary of Defense, the Air Force, and the National Reconnaissance Office. Their views on this matter were consistent. None of the national security organizations would formally object to human rating an EELV if that option were indeed chosen by NASA for its space exploration requirements. However, the concerns noted above were expressed and would need to be managed. The EELV program was initiated in 1995 in response to the Space Launch Modernization Plan and a subsequent National Space Transportation Policy PDD/NSTC-4. In 1998, development agreements were awarded to Lockheed Martin and Boeing to incorporate government requirements, both civil and national security, into their commercially developed variants of the Atlas and Delta launch systems. Since 2002, the Atlas V and Delta IV EELV vehicles have successfully demonstrated the ability to meet all of the key performance requirements of mass to orbit, reliability, and standardization of launch pads and payload interfaces. Because the low Earth orbit commercial satellite market envisioned in the early 2000 time period never materialized, the U.S. government is still the primary customer for the EELV systems, which are now operated by United Launch Alliance, a joint venture of Lockheed Martin and Boeing. In 2005, an acquisition strategy change was made to maintain launch and launch service capabilities for the Atlas and Delta under a firm fixed-price EELV launch services contract. This contract provides for a critical mass of sustaining engineering and launch production personnel, even when the launch tempo is slow. The DoD, Air Force, indicates that it is technically feasible to human rate the EELV systems, as verified for the committee by an independent aerospace corporation study. In doing so, there are several areas that must be addressed. These include production facilities. United Launch Alliance is currently consolidating its manufacturing capabilities in Decatur, Alabama. The possibility of human rating the EELV systems may add complexity to the planning for this consolidation, though the committee notes that United Launch Alliance has the experience and motivation to mitigate any launch processing. The aerospace study commissioned by NASA on human rating the Delta IV Heavy informed the independent assessment of launch system alternatives conducted for the committee. This study on human rating the Delta IV Heavy presented several options to minimize conflict between civil and national security space launch demands. The aerospace options include the possibility of utilizing the Orbiter Processing Facility and Space Launch Complex 39 at the Kennedy Space Center for processing a first-stage human-rated EELV. Such options need to be further evaluated. Cost. The increased production rates stemming from both a human-rated EELV and the National Security Systems variant of EELV should have a positive effect on United Launch Alliance hardware costs and reliability, as well as on the United Launch Alliance vendor industrial base. A more efficient procurement, surveillance, and mission assurance program should benefit both DoD and NASA programs. Further, the implementation of a human-rated EELV could accelerate the planned transition to a common upper stage for the Delta IV and Atlas V EELVs. Notwithstanding the cost opportunities, the implementation of a human-related EELV does introduce changes in the existing EELV baseline program. Therefore, a comprehensive management plan and structure with clearly defined responsibilities, authorities, and accountabilities must be formulated if this option is pursued. A similar approach would be required for launch scheduling. Industrial base. If a decision is made to human rate the EELV systems and NASA were to abandon the Ares 1 system but retain the Ares 5 heavy launch capability, the solid rocket motor industrial base would need to be sustained until the Ares 5 generated demand. The DoD may have to consider support to the solid rocket motor industrial base in recognition of both civil and NSS needs. If both the Ares 1 and Ares 5 programs were abandoned, a detailed civil and military analysis would need to be accomplished to ascertain the interdependence of technical and production capabilities between large solid rocket motors that are needed to support the nation's strategic strike arsenals and the large segmented solid rocket motors supporting human-rated systems for NASA. Findings on partnerships. International partnerships. The U.S. can lead a bold new international effort in the human exploration of space if international partners are actively engaged, including on the critical path to success. There could be substantial benefit to foreign relations, and more overall resources could become available. National security space. A desirable level of synergy between civil space efforts and national security space efforts should be reached, taking into account the efficient sharing of resources to develop high-value components, as well as the potential challenges in joint management of programs and reliance on a single family of launch vehicles in a class, for example, heavy lift. End of section 18. Recording by Lynda Neilson, Vancouver, BC.
Section 19 of Seeking a Human Spaceflight Program Worthy of a Great Nation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee. Chapter 9. Concluding Observations. No carefully considered human spaceflight plan, even when promulgated with the best intentions, is likely to produce a successful outcome unless certain principles are embraced in its formulation and execution. Some of the more important of these principles, generally derived from hard-earned experience, are summarized in this final chapter of the report. While not explicitly tasked to offer such observations, the committee believes that it would be negligent in its duty were it not to do so. 9.1. Establishing goals. Planning a human spaceflight program should start with agreement about the goals to be accomplished by that program. That is, agreement about its raison d'etre, not about which object in space to visit. Too often in the past, planning the human spaceflight program has begun with where rather than why. This is undoubtedly, at least in part, attributable to the fact that many of the benefits of human spaceflight are intangible, e.g., the positive impact the Apollo landing had during a time of great tribulation for America. But this makes such intangible benefits and activities no less significant. Witness the importance assigned to great literature, music, and art in our nation's history. 9.2. Matching resources and goals. Perhaps the greatest contributor to risk in the space program, both human and financial, is seeking to accomplish extraordinarily difficult tasks with resources inconsistent with the demands of those tasks. This has undoubtedly been the greatest management challenge faced by NASA in recent decades, even given the magnitude of technological challenges it has confronted. Consider the Constellation program as a case in point. While it is not clear to the committee what exactly was the official status of the funding profile NASA assumed in planning the program, there are differing views on this subject. It is clear that the amounts are smaller today by about one-third. It is also clear that when initiating decades-long projects of a demanding technical nature, some baseline funding profile needs to be agreed upon and sustained to the greatest extent practicable. In the Constellation program, the estimated cost of the Ares 1 launch vehicle development increased as NASA determined that the original plan to use the Space Shuttle main engines on the Ares 1 upper stage would be too costly, in part due to the need to add self-start, but the replacement engine had less thrust and inferior fuel economy, so the first stage solid rockets had to be modified to provide more total impulse. This in turn contributed to a vibration phenomena, the correction of which has yet to be fully demonstrated. This is the nature of complex development programs with budgets that are far more likely to decrease than increase. Complicating matters further insofar as the Constellation program is concerned, this committee has concluded that the shuttle program will almost inevitably extend its fiscal year 2011 in order to fly the existing manifest, the extension largely attributable to safety considerations, and that there are strong arguments for the extension of the International Space Station for another 5 years beyond the existing plan. These actions, if implemented, place demands of another $1.1 billion and $13.7 billion, respectively, on the NASA budget. In addition, adequate funds must eventually be provided to safely deorbit the ISS, funds that were not allocated in the current or original program plans. Shrinking budgets and inadequate reserves, the latter not only in dollars but also in time and technology, are a formula for almost certain failure in human spaceflight. If resources are not available to match established goals, new goals need to be adopted. Simply extending existing ambitious programs to fit the money is seldom a solution to the resource dilemma. The impact of fixed costs and technological obsolescence soon overwhelms any such strategy. In the committee's travels, it encountered widespread support for this policy of realism, although it is likely that most proponents were thinking of having more money, not less program. Should the latter turn out to be the case, much of that conviction is likely to vanish. In the case of NASA, one result of this dilemma is that in order to pursue major new programs, existing programs have had to be terminated, sometimes prematurely. Thus, the demise of the Space Shuttle and the birth of the Gap. Unless recognized and dealt with, this pattern will continue. When the ISS is eventually retired, will NASA have the capability to pursue exploration beyond low Earth orbit, or will there be still another gap? When a human-rated heavy lift vehicle is ready, will lunar systems be available? This is the fundamental conundrum of the NASA budget. Continuation of the prevailing program execution practices, i.e., high fixed cost and high overhead, together with flat budgets, virtually guarantees the creation of additional new gaps in the years ahead. Programs need to be planned, budgeted, and executed so that development and operations can proceed in a phased, somewhat overlapping manner. An additional action that would help alleviate the gap phenomena is to re-energize NASA's space technology program, an important effort that has significantly atrophied over the years. The role of such a program is to develop advanced components, for example, new liquid rocket engines, that can later be incorporated into major systems. Developing components concurrently with, or as a part of, major system undertakings is a very costly practice. A technology development program closely coordinated with major ongoing programs, but conducted independently of them, is preferable. 9.3. NASA Management Challenges. In planning to reach these lofty objectives with constrained resources, the question arises how NASA might organize to explore. The NASA administrator, who has been assigned responsibility for the management of NASA, needs to be given the authority to manage NASA. This includes the ability to restructure resources, including workforce and facilities, to meet mission needs. Likewise, managers of programs need clear lines of responsibility and authority. Management of unprecedented and complex international technological developments is particularly challenging, and even the best managed human spaceflight programs will encounter developmental problems. Such activities must be adequately funded, including reserves to account for the unforeseen and unforeseeable. Good management is especially difficult when funds cannot be moved from one human spaceflight budget line to another, and where new funds can ordinarily be obtained only after a 2-year budgetary delay, if at all. In short, NASA should be given the flexibility allowed under the law to acquire and manage its programs. Fixed overhead and carrying costs of NASA are currently helping to undermine what might be accomplished in new space endeavors. A significant fraction of what appear to be program-related costs in fact cover fixed and carrying costs of employees, facilities, and in some cases, contractors. This reality affects NASA in several ways. When a program such as the Shuttle is terminated, not all of the program funds actually become available to new programs. In fact, the fixed costs often simply move to the new program, where they continue to accumulate. When discretionary resources comprise a limited portion of overall resources, even modest program disruptions can have greatly magnified impacts. Significant space achievements require continuity of support over many years. One way to assure that no successes are achieved is to continually introduce change. Changes to ongoing programs should be made only for compelling reasons. NASA and its human spaceflight program are in need of stability, having been redirected several times in the last decade. On the other hand, decisions about the future should be made by assessing marginal costs and marginal benefits. Sunk costs can never be used as a reason not to change. The nation should adopt a long-term strategy for human spaceflight, and changes should be made only for truly compelling reasons. This report describes the advantages and disadvantages of each program option offered. The determination of whether and balance these exceed the compelling reason threshold is, of course, the essence of making a decision with regard to the future of the human spaceflight program. There is an often overlooked but vitally important part of the human spaceflight program that takes place here on Earth. This includes the contributions of the myriad engineers, technicians, scientists, and other personnel who work in NASA and industry. As Buzz Aldrin famously said, it's amazing what one person can do along with 10,000 friends. Special attention needs to be devoted to assuring the vitality of those portions of the workforce that represent critical and perishable skills that are unique to the space program. One example is the design and manufacturing of very large solid propellant motors. At the same time, it is demeaning to NASA's professionalism to treat the human spaceflight effort as a jobs program. Only a modest fraction of jobs generally fits the critical, perishable, and unique criterion. The NASA administrator needs to be given the authority to tailor the size of the NASA workforce and the number of centers employing that workforce to match foreseeable needs, much as is routinely done in the private sector under the pressure of competition. For example, when the end of the Cold War changed the role of the aerospace industry, some 640,000 jobs were terminated. Work should be allocated among centers to reflect their legitimate ability to contribute to the tasks to be performed, not simply to maintain a fixed workforce. NASA's relationship with the private sector requires particularly thoughtful attention. The two entities should not be in competition. NASA is generally at its best when innovating, creating, and managing challenging new projects, not when its talents are devoted to more routine functions. Industry is generally at its best when it is developing, constructing, and operating systems. 9.4. Systems engineering. If NASA is to successfully execute the complex undertakings to which it aspires, it must maintain a world-class systems engineering capability, a capability that this and other reviews have deemed to be marginal in its current embodiment. The dilemma is that the best systems engineers are often those with a great deal of experience, scar tissue, as it is often called by those in the aerospace industry. But how can one get scar tissue if one is confined to studying, analyzing, and overseeing the work of others? The answer, by and large, is that one cannot. One of NASA's answers to this dilemma, which has generated criticism in the past, has been to assume responsibility for developing selected major items of hardware internally, e.g., the Ares 1 upper stage. This, of course, places the institution in the hazardous position of serving at once as judge, jury, and potential defendant, as well as being in competition with those it manages in other arenas. Thus, NASA finds itself in the position of designing hardware, the engineering drawings for which are being produced by subcontractors to NASA to be handed over to a prime contractor to produce. This sort of formulation warrants exceptionally careful monitoring. It is fraught with opportunities for managerial conflict and technical incompatibility. A preferred approach for NASA to acquire a strengthened systems engineering capability would be to encourage or at least permit the movement of particularly talented individuals back and forth between government and industry, as often occurred during the Apollo program. This, however, is now discouraged or even precluded by today's government personnel policies, e.g., the long-time need for hiring well-intentioned but prohibitive conflict of interest policies, etc. Given this circumstance, the committee sees no ideal solution for maintaining a strong systems engineering capability at NASA. Perhaps the best among a generally limited array of choices is for NASA occasionally to take direct responsibility for relatively modest pieces of hardware, a responsibility that would not include making or subcontracting engineering or shop drawings for major items to be produced by others. It is noteworthy that the technology development program, cited elsewhere in this report, could be an effective training ground for systems engineers as well as program managers, all while maintaining risk at a manageable level. 9.5. Procuring systems. The committee has examined various future NASA system options and has observed that in many instances one of the more significant discriminators in development and operations costs is neither what NASA procures nor who supplies it, but rather how NASA procures and operates a system. The way NASA specifies, acquires, and uses systems, the tools NASA uses to manage its workforce, and the agency's authority to make purchase commitments all have a very large impact on what NASA can achieve for a given budget. Currently, NASA labors under many restrictions and practices that impair its ability to make effective use of the nation's industrial base. For example, NASA is commonly not allowed to change the size and composition of its workforce or facilities, which limits its ability to save money through the purchase of commercially available products. NASA has limited ability to shift funds between related projects to adapt to technical challenges without a protracted approval process. NASA is not permitted to make loan guarantees or employ other mechanisms by which it could create a market for commercial providers that might otherwise invest private funds in meeting some of NASA's needs. The Department of Defense has procurement rules that allow this. For example, NASA could very likely acquire propellant depots by making a bankable commitment to purchase propellant from such a depot, but depending on a promise from NASA today would almost certainly not be viewed as a reasonable risk by private investors. NASA is expected to undertake long-term projects with little hope of budget stability. With regard to human spaceflight, it is the committee's view that NASA can and should be the source of resource and technology, technology maturation, system requirements, systems architecture, procurement oversight, exploration operations, expensive multiple-user facilities. NASA generally should not be its own supplier. Numerous studies have shown that any organization, public or private, that is its own supplier lacks much of the incentive to deliver the most cost-efficient product. Today, NASA has many options available to procure systems innovatively. These include, but are not limited to, commercial purchases, Space Act agreements, COTS-like cost-sharing agreements, prizes for innovative technologies, and others. Determining the requirements for an engineering project while it is being built inevitably leads to a very expensive result. Requirements should be clearly established prior to beginning engineering development. Work that contains significant risk or for which scope cannot be accurately defined is generally best performed under cost-reimbursable contracts. Work with scope that can be accurately defined should generally be conducted under fixed-price contracts. The committee is convinced that NASA can substantially increase the opportunities for entrepreneurial, commercial involvement in its space programs by more aggressively utilizing the commercial authorities already granted to the agency, and by adopting benchmarks in commercial practices utilized in other federal agencies. 9.6. Managing the balance of human and robotic spaceflight. Although the committee was tasked only to address the human spaceflight program, including robotic missions that are specifically encompassed within that program, it is appropriate to comment about the role and synergy of human and robotic exploration as a whole. The committee believes that America is best served by a complementary and balanced space program involving both a robotic component and a human component. The robotic portion is often but not exclusively associated with science missions. Without a strong and sustainable science program, the means of acquiring fundamental new knowledge, any space program would be hollow. The same can be said of the absence of a human spaceflight program. Humans in space on new and exciting missions inspire the public, but so do the spectacular accomplishments of such robotic spacecraft as the Hubble Space Telescope, the Mars rovers, the Earth Observing System satellites, or the twin Voyager spacecraft that are poised to reach interstellar space. This is to suggest that both the human spaceflight program and the science program are key parts of a nation's space portfolio. Needless to say, robotic spaceflight should play an important role in the human spaceflight program itself, reconnoitering scientifically important destinations, surveying future landing sites, providing logistical support, and more. Correspondingly, humans can play an important role in science missions, particularly in field geology, exploration, and in the maintenance and enhancement of robotic systems in space. It is in the interest of both science and human spaceflight that a credible and well-rationalized strategy of coordination between the two types of pursuit be developed, without forcing unwarranted intermingling in areas where each would better proceed on its own. Robotic activity in space is generally much less costly than human activity, and therefore offers a major inherent advantage. Of even greater importance, it does not place human lives at risk. Astronauts provide their greatest advantage in the most complex or novel environments or circumstances. This will be the case in the exploration of planetary surfaces and in repair or servicing missions of the type undertaken for the Hubble Space Telescope's primary mirror. In contrast, the value of humans in space is usually at its minimum when they are employed transporting cargo. The bottom line is that there are important roles to be played by both humans and robots in space, and America should strive to maintain a balanced program incorporating the best of both kinds of explorers. That said, there are nonetheless inevitable conflicts that arise from the competition among programs for resources, particularly financial resources. It is therefore of the utmost importance, if balance is to be maintained, that neither the human program nor the robotic spaceflight program be permitted to cannibalize the other. This has been a significant concern in the past, particularly given the size of the human spaceflight program. Difficulties in the human space program too often swallowed resources that had been planned for the robotic program, as well as for aeronautics and space technology. Robotics are generally, although not exclusively, considered to be of greater interest to the scientific community. It is essential that budgetary firewalls be built between these two broad categories of activity. In the case of the International Space Station, one firewall should be the establishment of an organizational entity to select endeavors to be pursued aboard the space station. Without such a mechanism, turmoil is assured and program balance endangered. Findings: the right mission and the right size. NASA's budget should match its mission and goals. Further, NASA should be given the ability to shape its organization and infrastructure accordingly, while maintaining facilities deemed to be of national importance. Robotic program coordination. The robotic and human explorations of space should be synergistic, both at the program level, e.g., science probes to Mars and humans to Mars, and at the operational level, e.g., humans with robotic assistance on a spacewalk. Without burdening the space science budget or influencing its process of peer-based selection of science missions, NASA should proceed to develop the robotic component of its human exploration program. Management authority. The NASA administrator and program managers need to be given the responsibility and authority to manage their endeavors. This includes providing flexibility to tailor resources, including people, facilities, and funds, to fit mission needs. Stability in programs. In the most recent decade, NASA has spent about 80% of the GDP deflated budget that it had in the decade of Apollo. Recurring budget ambiguities and reductions and redirections of policy, coupled with the high fixed cost structure of NASA, have not optimized the return on that investment. Right job for the NASA workforce. NASA has a talented but aging workforce. NASA should focus on the challenging long-term tasks of technology development, cutting-edge new concepts, system architecture development, requirements definition, and oversight of the development and operation of systems. Fixed operating costs at NASA. There are significant fixed costs in the NASA system. Given that reality, reducing the funding profile much below the optimum for the development of a given program has an amplified effect of delaying benefits and increasing total program cost. NASA's fundamental budgetary conundrum. Within the current structure of the budget, NASA essentially has the resources either to build a major new system or to operate one, but not to do both. This is the root cause of the gap in capability of launching crew to low Earth orbit under the current budget. It will likely be the source of other gaps in the future. Commercial involvement in exploration. NASA has considerable flexibility in its acquisition activities due to special provisions of the Space Act. NASA should exploit these provisions whenever appropriate, and in general encourage more engagement by commercial providers, allocating to them tasks and responsibilities that are consistent with their strengths. 9.7. Concluding summary. NASA is the most accomplished space organization in the world. Its human spaceflight activities are nonetheless at a tipping point, primarily due to a mismatch of goals and resources. Either additional funds need to be made available, or a far more modest program involving little or no exploration needs to be adopted. Various options can be identified that offer exciting and worthwhile opportunities for the human exploration of space if appropriate funds can be made available. Such funds can be considerably leveraged by having NASA attack its overhead costs and change some of its traditional ways of conducting its affairs, and by giving its management the authority to bring about such changes. The American public can take pride in NASA's past accomplishments. The opportunity now exists to provide for the future human spaceflight program worthy of a great nation. End of section 19. End of Seeking a Human Spaceflight Program Worthy of a Great Nation by the Review of U.S. Human Spaceflight Plans Committee.